Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. In this section, this is the continuation of the previous lecture where we are describing the different kind of boundary condition that is applicable for electromagnetic wave. So we are going to continue with this our previous lecture. In the previous lecture we have described the dielectric boundary conditions, and from this lecture now on we are going to describe how all those factors, all the different parameters of magnetic and electric field are work or function in a dielectric conductor media interface. So let's begin with the lecture. Okay, so where we are is that we have described dielectric boundary condition. In this section we are going to describe conductor dielectric boundary condition. Now what we have here is the same thing. In case of conductor, now we have to consider few things. Now as we have described dielectric boundary condition, in case of dielectric we have already knew what kind of parameters are working there. In this dielectric medium here we have E, and this is the electric field vector. It has one tangential component, another one is a normal component. This is the specific space that we have already described. This is the ABCD path, which has a del H height, infinitesimal small height, infinitesimal small width, and the dielectric value will be F psi is equal to F psi 0 into F psi r. R is the relative dielectric and this is the dielectric constant at free space. Now if we consider in here the conductor, in case of a medium that is conducting, so in case of conducting medium what we have there is that if the conductivity will be infinite because there is a conductor. Now we have already knew that the J is equal to mho into E. Now J is the conduction current density. Now conduction current density is the multiplication of conductivity into electric field. Now in case of a conductor, we are already have described that in case of conductor that conductivity will be infinite. So to get a finite value of conduction current density J, if we have conductivity which tends to infinite, to get a finite value of conduction current density we need to have a value of electric field intensity which should be tends to 0. Without that condition approved, we can't have a finite value of conduction current density. So in case of conductor we have a conductivity which is infinite, and we also have electric field intensity which is tends to 0. So through which we can get a conduction current density which has a finite value. So from this understanding we can let's go to the next slide. In this next slide the same thing is applied here, that in conductor dielectric boundary condition we also understand that conductor value E, electric field intensity is 0, and these conditions are very much similar to the previous one, that each has a displacement vector which has a tangential value and normal vector. In case of electric field intensity, which has a tangential value and also a normal value. So these are the conditions. So let's go to the next slide. And now in case of conductor dielectric boundary condition, we have that the interface between a perfect conductor and a dielectric shown from that. We have already show all those things in the figure, and apply the equation closed path integration of E dot dl, the dot product of electric field and infinitesimal small length, which is equal to 0 to path ABCD in the figure. From this equation we have Et del W minus En del H by 2 minus 0 dot, because in case of conductor medium that the E is 0, so this 2 value will be 0, this value also will be 0, and En, this normal vector, this tangential vector is the tangential component, normal component of electric field intensity of the dielectric medium. So in case of dielectric medium, all the tangential vectors and the normal vectors are realized or present, but in case of conducting medium or conductor, the electric field tangential in electric field, as the electric field vector is not present, so the normal vectors and the tangential vector will also not be present. So from this equation what we have here is that this and this vector will cut yourself out, and we get Et del W is equal to 0. And from that we have already known the del W is that infinitesimal small width. So from this we can realize that tangential component of electric vector in case of dielectric medium is 0. And also, as it is 0, the tangential component of electric field intensity is 0 in case of dielectric medium. The same thing will also applicable to displacement vector, but the tangential component of displacement vector of dielectric medium is also 0. From this we get that dt is equal to f psi 0 into f psi r into er, and it's also 0. So this is the equation that we can extract from the conductor dielectric boundary conditions. And what we have here, the boundary condition for the normal components are obtained by the applying Gauss's law on a small pillbox shaped volume as in the figure, that d dot ds, the dot product of the surface integral of dot product of displacement vector and infinitesimal small surface, is equal to the total charge enclosed in the surface. From this we also get that dn is equal to rho s. Basically what we have here, that in case of conducting medium, what we have, that E is equal to 0. So as the electric field intensity is 0, the displacement vector will also be 0 in case of conductor. But as we know from the dielectric boundary condition, that dn1 minus dn2 is equal to surface charge density that we have here. But in case of conductor dielectric medium, dn2 is not present. So from that we can conclude that the normal vector normal component of displacement vector in case of dielectric medium is equal to the surface charge density of that specific surface that has enclosed the surface charge density enclosed by the net surface charge density enclosed by the surface is equal to the normal component of displacement vector which is present in the dielectric medium. So this is the equation that we have concluded or extracted from the conductor dielectric boundary condition. Okay. From this we will go to the next slide. Now, so what we have here, the conductor dielectric boundary condition, no electric field exists inside a perfect conductor. External electric field, if any, is normal to the conductor surface, as given as Tn is equal to rho s. So this kind of media interface, the boundary condition will be applicable for in case of waveguide or optical fiber, where the core through which the signal being carried or the electromagnetic wave being carried is a conducting medium, and the cladding part is a dielectric medium. So the conductor dielectric boundary condition will be applicable in case of optical fiber and waveguides. So this is what you have understood from this slides. Okay, so let's go to the next slide. Now if we consider the conductor free space boundary condition, it will be much more easier. That is a special case for conductor dielectric condition, that it can be obtained by replacing f psi r is equal to 1 in the equation, that dn is equal to f psi 0 into En, normal component of electric field, which is equal to rho s, or the surface charge density. So the normal vector of normal component of displacement vector is equal to the surface charge density, and the tangential component of displacement vector is also equal to 0. So in case of it means the tangent in case of conductor free space boundary condition, the tangential component of displacement vector will be 0, Vt is equal to 0, and normal component of displacement vector is equal to the surface charge density of that space which has been enclosed by the area. So this is the equations. Okay. So let's go to the next slide. Now this is the pictorial description of the conductor free space boundary condition, where the free space is f psi is equal to f psi 0 to f psi r, and in case of conductor, its value will be equal to 0. So anything that any electric field or displacement vector will be present in free space. In the case of conductor, we have already know that E is equal to 0 to get a finite conduction current density. As we know, the conductivity will be in infinite value. So electric field intensity should be tends to 0. So from that we can get a finite value of conduction current density. So in case of conductor, E is equal to 0, and in case of free space, these components are present, that E is electric field intensity, and this is the displacement vector, and these are the components which are along the same path. So this is an also important factor that we have to realize, that basically the displacement vector in case of an isotropic medium, basically the displacement vector is very much similar to the electric field intensity, because in case of isotropic medium, the the value of f psi will be constant throughout the medium. So it will just act as a constant. So it can be easily deducted that d is proportional to the d is nothing but a very much similar vector component, a vector of as E. So D and E is basically a same vector. So that we have concluded here. Okay, so let's go to the next slide. So up to this point, what we have described is that the electric field intensity and displacement vector of dielectric boundary condition and dielectric conductor boundary condition. And from all those mathematical expression, we have realized that normal component of displacement vector of medium 1 minus normal component of displacement vector of medium 2 is equal to the net surface charge density, which can be obtained from the total charge that has been enclosed in the surface through which all those components are getting in and getting out. And another mathematical expression we have realized that in case of dielectric boundary condition, that ET1, the tangential component of electric field intensity of medium 1 and tangential component of electric field intensity of medium 2 is equal. Now, as we have from that dielectric boundary condition, as we jump to the dielectric conductor boundary condition, we have realized that in case of dielectric boundary condition, the value of normal component of displacement vector of medium 1 is basically equal to the surface charge density. It means if any surface is present in the boundary, we will have a discontinuity in case of displacement vector, and in case of tangential component of electric field intensity, the values will be continuous, because along the boundary the electric field intensity, the tangential component of electric field intensity are continuous. So as we have also understand that displacement vector and the electric field intensity both are basically the same vector. So through with that we have described the tangential components and the normal components of both the physical interpretation. From the both we can describe the normal component and the tangential components of the displacement vector and as well as the electric field intensity. So for that part, the electrostatic part has been covered. Now if we just jump back to this current slide here, that we have here the same condition, now we are going to describe all this condition in case of magnetic boundary condition. It means the boundary condition according to the magnetic flux density and magnetic field intensity. Now we have here what, that this is the B is the magnetic field intensity, this is a magnetic flux density vector, and it has a normal component and it's a tangential component. And this is the medium 1 and this is the medium 1. We will have the same thing. I am not going to repeat that this is the medium 1 which has a different mu 1 permeability. This has a different medium 2 which also has a different permeability. It means the mu 2 is not equal to mu 1. So this is also a magnetic flux density which has normal component. This is the normal component Bn2, this is the Bt2, and we can describe it using a boundary. This is the boundary, this is the surface, this is the vector, this is the Bn1 magnetic flux density, and this is the Bn2, and this is the del H2 and del H2. Now from Gauss's law, you can describe here, and we will describe it in the next slide here, is that magnetic boundary condition, what we have here is that consider the boundary between two isotropic homogeneous linear materials that we have already described with permeabilities mu1 and mu2 at the boundary, is that at the boundary the magnetic flux density B may be decomposed into normal components Bn and the tangential component B2. Applying Gauss's law for magnetic field on a small pill box of shaped volume, it could be any kind of shape that we can extract as according to our understanding. The surface integral of the dot product of magnetic flux density and infinitesimally small surface is equal to 0, which we have already described in the Maxwell equation, the second Maxwell equation, where we have described the divergence of magnetic flux density is equal to 0. From that specific conclusion, we can extract the relation between the Bn1 del S minus Bn2 del S is equal to 0, where the Bn1 is equal to the Bn2. Because as we have already known that if there is a surface which contains a magnetic charge, suppose countless magnetic charge, suppose 10, 20 or 2000 magnetic charge, from that we can realize that the positive and the negative magnetic charge will be placed within that specific surface area. So from that understanding, we can conclude that the normal component of magnetic flux density of medium 1 is equal to the normal component of magnetic flux density of medium 2. It means in case of boundary condition, if you consider the boundary condition, the magnetic flux density is continuous in boundary. It means the normal component of B is continuous across the boundary between the two adjacent medium. So from that we have described this situation. Okay. So let's go to the next slide. This is the boundary condition that we are talking about, the magnetic boundary condition. The B2 minus B1, which has two different components. One, if we take an alpha, it means the B2 minus B1 dot A suffix n is equal to B2 minus B1 dot 1 dot cos alpha, which is equal to 0. From that boundary condition, we can understand that Bn1, the normal component of magnetic flux density of medium 1, is equal to the normal component of magnetic flux density of medium 2. From that, we can realize that in the boundary, both magnetic flux density are continuous. Okay. So from that equation, we can understand again that Bn1 can be written as mu1 Hn1 and Bn2 could be written as mu2 Hn2. From that equation, we can also write that magnetic field strength, normal component of magnetic field strength of medium 1 is 2. Magnetic field intensity, normal component of magnetic field intensity of medium 2 is equal to the mu2 by mu1, and where the mu2 is the what? It is the dielectric constant. It is the permeability of medium 2, and mu1 is the permeability of medium 1. So from that we can conclude that normal components of magnetic field strength H are not continuous across the boundary, because we can understood that Hn2 is equal to mu1 by mu2 Hn1. It means Hn2 is not proportional to Hn1. Depending upon the permeability of this two medium, the Hn2 will be different. So from that equation you can understand that magnetic flux density along the boundary will be continuous, but it is not true for magnetic field intensity. In case of magnetic field intensity, the value of H will not be continuous along the boundary. Right? So the normal components become continuous only when mu1 is equal to mu2. Supposedly the mu1 is equal to mu2 will happen only when this medium is basically one medium. So in that case, there is no boundary between the two materials. So mu1 is equal to mu2 basically provided us the information that if there is no boundary between two medium, it is basically a one medium. So if the medium is different, the magnetic field strength are not continuous in boundary region, but magnetic flux density are continuous in a boundary region. Now this will also be very much similar to if you are talking about the electrostatic perception. In case of electrostatic theories, that tangential component of electric field of medium 1 and medium 2 are continuous in boundary region. That's why the ET1 is equal to ET2. And the same thing is applicable for BN1 and BN2. But in case of DN1 and DN2, those are not continuous in the boundary region. That's why the equation that we have described here, that dn1 minus dn2 is equal to the surface charge density, rho s. So let's go to the next slide. So from this equation we have understood that magnetic boundary condition can be written as the tangential and normal components of medium 1 and medium 2. These are the pictorial depiction that we have already described here. Now what is the del L, how this works, how the integration works. So let's go to the next slide. So from this equation what you can get that now the construct a closed contour C across the boundary and apply Ampere's circuital law for this closed path. So what we will get here is that closed integral of H dot dl is equal to the total current enclosed by the surface. So now if you have to describe with mathematical condition here, that tangential magnetic field strength into del L plus Hn2 into del H by 2 plus Hn1 into del H by 2 minus Ht1 del N minus H1 del H by 2, that we have already described earlier, so we don't need to elaborate the explanation here. Is that is equal to Kn del N into H22 del N1 minus Ht1 del N is equal to Kn del N, because all the other components will cut each other out. So from that we can get that tangential component of medium, the magnetic field intensity of normal component of magnetic field intensity of medium 2 minus the normal component, tangential component of magnetic field intensity of medium 1 is equal to the Kn, where the Kn is the component of K normal to the plane of the closed path. Tangential component of H is a discontinuous across the boundary between the two adjacent media. So from this we can get that the tangential components of magnetic field strength are not continuous in boundaries. So we have concluded that Ht2 minus Ht1 is equal to K, Ku or Kn. Okay, so let's go to the next slide. So magnetic field boundary condition can be also be written as the above condition equation may be written in the vector notation is that the H2 minus H1, all those are vector, the curl of that specific unit vector is equal to the K. If both the media across the boundary are not conductors, then K is equal to 0. So the tangential component of magnetic field strength is continuous across the boundary between the two adjacent media if K is equal to 0. It means the value of K, if the value of K is 0, then the tangential component of magnetic field strength will be continuous across the boundary, and it could be understandable if the media one is dielectric, another one is a conductor. So the boundary condition in case of dielectric and conductor media interface, this condition that has been written here can be obtained. This equation, this tangential component of magnetic field intensity of medium 2 and the tangential component of magnetic field intensity of medium 1 is equal. So from this we can understood that if the medium is a dielectric conductor media interface, if both in case of that the tangential components are continuous. So this is the okay. So the same thing that we have already discussed, this is the pictorial depiction that we have understood, that from this we get this K, H1, T2 minus H2. We have already described this all these things. So in the magnetic boundary condition we have this. So the tangential component of the same thing will be occurred, because we have already understood that magnetic flux density is basically nothing but the product of permeability and the magnetic vector field magnetic field intensity. So as we can understood that we are using isotropic medium, and the syllabus we have here is we are considering the isotropic mediums. So the B is proportional to H. The magnetic flux density will be equal to or the proportional to magnetic field strength. So all these will be identical. So if we are considering anything along to the magnetic field strength, so tangential component, it will also be true for magnetic flux density. And if one thing is considering true for magnetic flux density, which is also be considering true for magnetic field strength, and this is also be applicable for electrostatic conditioning. So this is, we have already described all these things, and the same mathematical calculation will be used here. So we know this. So this is the medium 1, medium 2. From this equation we will get the tan theta 1 by tan theta 2 is equal to mu 1 by mu 2. This is the law of refraction that we have described also earlier in case of electric boundary condition. So both are basically identical to each other. So this is where we are going to conclude our session or lecture, and using this three explanation we are concluding the module 1, where we have covered, or we have tried to understand the magnetic and electric boundary condition and the Maxwell's equation. So okay.